Well, dear, so welcome back. So today is a very auspicious day, as you know. 75th year of our independence. Great nation, great country, and I congratulate all of you on this very special day. And I hope you are enjoying, and let us also enjoy a little bit about with this listening this lecture, wonderful lecture on. We'll continue our discussion on how to model a now type humanoid robot. As you have, by this time, you already know that humanoid robots are special types of robot. They are not so precise, and they have intelligence, and they can share our social space. And in that context, now is one such robot. Okay, at least for research and teaching community as on date. Okay, so we are studying how to actually model, mathematically model now type of humanoid robot. So um, you have seen that the robot has several joints and all kind of things. We have already told you in my earlier lecture. But here we can analyze them or model them using some divide and conquer principle. In that sense that let us segregate head. Okay, so head has two joints, pan and tilt, or roll and yaw, pitch and roll. Okay, or sorry, pitch and yaw. So whatever way you can describe, basically they have two revolute joint as depicted here. And in my earlier class, I told you using de Novet-Hartenberg notations how to model such robot. Today we'll further continue our discussion, and we will learn how to model the arm. Okay, and arm has mm, 1, 2, 3, 4, 5. Actually, there are 5. 1, 2, 3, 4, 5. 5 degrees of freedom arm has, and they have been depicted here beautifully. Okay, so here is a coordinate frame attached. Okay, so this is 0th coordinate frame, first coordinate frame. Okay, second coordinate frame, third coordinate frame, like that. So so these are the 5 joints we have, and this is very, very wonderful and important schematic diagram or skeleton or for studying the now robot anatomy, which you have got from manufacturer, and once you have got, you can use it for actually modeling. So we have just segregated head, yaw and pitch, right arm, okay, right shoulder, pitch and roll, elbow, yaw and roll, and wrist, yaw. Okay, so yaw, roll and pitch I have also described. So these are convention, right? Basically this has revolute joints. Okay, so left hand also is a symmetrical. Okay, so similarly right leg, left leg, these are the degrees of freedom it has. Right now we will concentrate on, actually we will concentrate basically on arm. Okay, how to model arm. In my earlier class I have told you how to model head. So head already we have modeled. So today we will be modeling either left or right arm, because they are symmetric. So there will be no difference in modeling. We will show it. Okay. So what we will have to do, basically from the coordinate frame as had been attached here. You see, left arm joint 1. This is joint 2. Okay, joint 3, joint 4. Okay, and this is joint 5. So you have this is the wrist joint, and so these are the 5 degrees of freedom it has, and accordingly the coordinate frame has been attached. Z axis is always aligned in the direction of motion. Okay, wherever you find motion axis, you assign Z axis. So those things are repetitive in nature, but they are important to know. So this is what you need. This is what you need. This is a mother matrix. Okay, we have deduced it. Okay, from de Novet-Hartenberg principle, and using this matrix, using this coordinate frame attachment, we are going to now do the modeling, forward kinematics modeling of NAO's arms first. Okay, so first of all, arm, right arm. Okay, so this is ith link. This is your the twist angle. This is the common normal, the distance between common normal, and this is the motion axis. Okay, so you see, so right arm, okay, where here it is pi by 2, right? So you see, so this is what you have seen here. There is a twist angle minus pi by 2, Here see, Z0, so Z1 and Z0, the angle between them is minus pi by 2. Okay, so this has been depicted here, and all other parameters are 0 except theta 1. So that's how coordinate frame has been attached. So this is you must know, and just go back, see how the coordinate frame attached, and coolly you verify that these are correct. Okay, this is very important to have this table drawn very correctly. Okay, so any mistake you see will be dangerous. So these are the upper arm length, lower arm length, these are some offsets. So this you can also refer. Okay, you will have to actually refer when you are drawing the DH table. So this is Dinovate Hartenberg table for right arm. So this is again DH table for now left arm. So similarly, DH table for now left leg, and this is DH table for now left leg. Okay, this is right leg. So very beautifully, first we'll show you that for right arm, minus pi by 2, all are 0, theta 1, pi by 2, this is the twist angle, okay, and then pi by 2 plus theta 2, because the theta 2 is making always an angle by construction, okay, pi by 2, so this is has to be added, okay, all kind of thing. And this is the upper arm length, which is 105 millimeter in millimeter, and this we are measuring all in radian. So this is the way, very simple, you complete the table for right arm. Exactly same, nothing is different. Just I have to grow your confidence, I have drawn again. Okay, so you just see here, and you need to see from here. So these are the length, upper arm length, lower arm length, which you are observing here, upper arm length, lower arm length, okay, in appropriate coordinate frame. And that's it, the Dinovate-Hartenberg table. Now regarding leg, there is a little bit, you'll have to be careful, okay. So left leg, you see, this is actually second link Z. This is the angle 45 degree. Okay. So with respect to this, so you see, you can see with respect to this, what is the angle between this Z axis and this Z axis, or this Z axis and this Z axis? Tell me. This one, that is pi by 2 plus this one, pi by 4. Okay, so 3 pi by 4, and the angle is minus, because clockwise this Z axis is deviating from that Z axis in clockwise direction by an amount 3 pi by 4. So when carefully you must put this value. Okay, when, so left leg has this speciality. Okay, so this is what I was talking about. Okay, be careful. And most of the thing, and right leg has no such thing, right leg, you see this is the leg, so this is 45 degrees. So angle between z axis, this and this z axis, between two z axis is 45 degree in clockwise direction. Okay. Um, so actually, so you have got pi by 4 and all kind of thing. Similarly, pi by 2 this way. So this is the way you should. So 100 is the thigh left, and this is 100. 2.9 is actually tibia. You can see for all this 100 2.9. Okay. So this is tibia length. Thigh length is 100 millimeter. So 100 millimeter, and we have kept it minus because it is actually the z axis is in this direction, and you are measuring in this direction. So here is the origin. So this is minus direction, negative z direction. Okay, so that's why. So with this, I think you have understood. If still you have doubt, then you just I am keeping this drawing with you. You just in a cool situation, you just quietly you see how the coordinate frame has been attached in the leg, and try to verify it. Okay. So this is the step 1, most fundamental one. Well, so all the DH table has been prepared correctly. And now whatever you want, you take that DH table and model. It's as simple as this. Say, I would like to model now. Now, right arm. So corresponding to right arm, this table I have copied and put it here. And this is my matrix. Okay. So step by step, you come here. This is an arrow showing the link, fast link. Okay. So these are the parameters. DH parameter, you put those values here. Okay. So the motion parameter is theta 1. So cos theta 1 minus sin theta 1 0, and AI minus 1 is 0 for the first link. Okay. So that's how first row of this first row, that is, you are calculating the transformation matrix of link 1 with respect to ground link, which is put somewhere here. Okay. So here you have, so it is shown here. Okay. Somewhere here. Okay. So 0th link. Now come to the second row. Oh, sorry. Second row of this matrix. Second row. So first row is this. Okay. Second row, you see, sin theta 1, cos alpha I minus 1. So you put this cos of minus pi by 2. Then similarly cos theta 1, cos of minus pi by 2, minus sin minus pi by 2, okay. And then since d1 di is 0, this is 0. And then come here, okay, corresponding to this row, sin theta 1, sin minus of pi by 2. Very simple, yes. Cos theta 1, sin minus pi by 2, cos minus pi by 2, 0, 0, 0, 0, 1. And you are getting this matrix. Okay. So this is actually link 1 with respect to 0. Similarly, link 2 with respect to 1. So you will have to come here, take all the parameters and put it there. Okay. Put it there, and you will end up. So please check. Okay, carefully I have done, so please check, you will get this matrix. Similarly, T3, come here, with respect to 2 you will get, and then come here and you will get T4, 54 with respect to 3. So you are getting, right? I equals to 4, put I equals to 4. So 4 with respect to 4 minus 1, 3. That is the matrix which you are getting. Transformation matrix of fifth link with respect to fourth link will be given by this row, all the parameters, okay? And then you see this is minus because they are measured, they're measured about negative direction of y, okay? So this is, you put, sorry, so this is the DH table. You just simply put this and you get 5 with respect to 4. Clear? 5 with respect to 4. Minus is because of this. DI is actually 55.95, but since sign of minus pi by 2 is there, sin pi by 2 is 1, so minus sign remains. That's why the minus is coming. Well, so that's it. And you have got the first arm. This is my arm, okay? Right arm's model, okay? Right arm model. So these parameters, time to time, you should see, okay? The coordinate frame and these values are very, very important. We are taking from here, okay? We explained the other lecture, okay? And then again do the same thing for left arm. So here is left arm, okay? Exactly the same transformation matrix. In a similar way, you have modeled the left arm. Now, after modeling, we need to just convince ourselves that modeling is correct. That means coordinate frame we have put in a correct way. So how to do that actually? So what you will have to do, you will have to put this so put all this for checking na, put all the configuration value to 0. Okay, so robot is actually in this position, means hands are like this. So all these configurations are 0, and so this will be in a folder, in a straight arm hanging from the body is the configuration where all the theta values we are putting 0. And then you will see that in doing so, you are getting, you will get something like this 5 with respect to 0, that is 0, 0, 1, and you see 105 and 55.95. So 0.95, 160.95. So 100.95, 1, 0, 0, 0, 0, 1, 0, 0, and 0, 0, 1, 0, 0, 0, 1. Okay, so you will get put in. So what you will have to do, you will have to just put all this theta 1, theta 2, theta 3, theta 4, theta 5 to 0. Okay, and then multiply all these matrices. Okay, and you will end up in getting this. Okay, now to check, you see 105, 55.95, 105 upper arm length, and upper arm length and lower arm length. So this will be hanging in a straight way, na? So this will be plus this, okay? So this is what actually you should get. You should get. So you have got this, and this is the sum matrix, as you know, which is rotation matrix. And since all configurations you have kept 0, the rotation matrix should be actually should be of this nature: 0, 0, 1, 1, 0, 0, 0, 1, 0. Okay. So in actually this is rightly so, because if you check, just you check x5 dot y0 equals to y5 dot x0 equals to z5 dot x0 equals to 1. That means all the direction cosines are 0. All the direction cosine equals to 0, as it should be in this special configuration. Okay, so that's great. So you have put some effort and just multiplied, and multiplication will not be that difficult because you are putting all this theta 1, theta 2, theta 3, theta 4, theta 5 values to 0. That means cos 0 will be 1, so sin 0 will be 0, so the matrix will be much more simpler, and the multiplication will be easier, and you should get the matrix like this. Okay. Here you can check that this is x5 dot y0 equals to y5 dot x0 equals to z5 dot x0 equals to 1. That is all the direction cosines equals to 0. Once you got this, then you can just infer that, well, I have whatever I have done, I have got the result, I have correctly assigned my coordinate frame, and I have got the results, and everything is correct, because this has to be written correctly. And once it is written correctly, then with this forward kinematics of arm, then you can, just using choreograph software, you can move the arm like the way you want, just running several loops. Okay, so you have all the angles range, okay, again given. Okay, so all the angles range are given. Run the loop within that range, okay, and you can move using forward kinematics. You can figure out the working envelope. You can simulate. Okay, in fact, there is a software called choreograph software. We have the license one, but you can get 1 month trial version to just practice that. You can design beautiful posture of the limbs of the robot. You can move around with the limbs of the robot using that choreograph software. Okay, so that's it for today. We have today learned how to beautifully mathematically model the now left or right arm. Okay. Next, we will study how to model right leg and left leg for now. Okay. Till then, stay safe and enjoy. Wish you all the best. Bye bye.